Welcome to the technical breakdown of the 2028 smoke measurement trials. Today we are evaluating the performance of two octa-ring smoke measurement systems. The Alpha, featuring the OPT4048 tri-stimulus sensor, and the Rainier, utilizing the TCS34725 RGB sensor, as well as the MAX 30105 sensor. By stacking these devices, we've conducted a side-by-side comparative analysis to validate sensor accuracy and explore new power-saving efficiencies. Our methodology involves synchronizing both devices for time series analysis, while the Alpha uses a higher accuracy tri-stimulus tech. The Rainier relies on a more common RGB sensor. To ground our data, we also track the stove shell and gas temperatures to correlate combustion phases with smoke events. The highlight is that the opacity correlation was 0.916, tracking from 0 to 99%. The results were impressive. We observed an opacity correlation of 0.916, while the Rainier shows a slightly higher mean opacity at 14.3%. The Alpha trended slightly higher during high smoke events, averaging 80 opacity compared to the Rainier's 75.9. Despite these minor offsets, the sensors showed nearly identical behavior across the entire range. We also analyzed color shift. Both sensors showed a strong correlation here at 0.824. This spectral signature is driven by the red to blue ratio because the blue light scatters more easily than the red in the presence of small particles. The blue diode signal drops faster. This wavelength-dependent scattering allows us to identify not just the density, but the characteristics of the smoke particles. The data confirmed a classic thermal trend. As the stove shell temperature increases, opacity decreases. Interestingly, the stove's thermal mass, the shell, was a more reliable indicator of burn cleanliness than the stack gas temperature. A hot shell indicates established, efficient combustion. These next two graphs are a reference of opacity versus stove temperature, and we've been able to determine for this system that keeping it above or around 350 degrees Fahrenheit, we have the lowest opacity numbers. We can use this data to develop an algorithm for this stove to control near this 350 range, so it won't go too much above that, and it'll alarm the operator when it needs to be refueled. We have completed our work with the DOE-funded grant where we worked with the University of Berkeley. We had 2 scientists and a few interns. We had monthly reports, we did a lot of work, and they came up with some inadequacies or problems they had with the system that had to be resolved. And we believe we've resolved most of these inadequacies. The sensor life with the new OPT sensor it lasts months out in the field. And we didn't have problems like they did with the TCS sensor. We have evidence of success and versatility. We can change out the sensor and it records predominantly the same. The research demonstrates that an optimized opacity sensor can accurately measure smoke in real time. A key breakthrough is showing the system is adaptable. We can interchange sensors. We can put in ultraviolet sensors, visual spectrum wavelengths, UV. We can change things around. We've used narrowband green light sensors. They work just fine. And we can tune the system in. It's talking to the combustion air controller, and we can give the combustion air controller the information it needs to do a clean burn. The opacity system only needs to be installed for maybe a week or 2, and then the system can learn how that stove burns the cleanest. This is the way to take a system that's been installed for 20 years and make it burn clean and efficiently. You do it by measuring emissions.